Today, I am going to give a lecture on design of machine parts against static loads. So, as we all know, majority of our machine parts, they're all made with the ductile materials. So, why? Because ductile materials, they undergo some kind of visible deformation before their failure. They give a kind of warning before its failure, so that a design engineer, he can make some corrective action, he can replace the damaged part. But actually, we can divide the engineering materials into two types. One is a ductile material and another one is a brittle materials. I can say 95% of the machine components, they're all made with ductile materials. And to the maximum extent, we are limiting the applications of brittle materials for making of machine components, because brittle materials, they fail suddenly without giving any warning. That is the reason. But what for we are using this brittle materials? We are using brittle materials only for the casing of the machinery as well as for the bed of the machinery, right? Because this brittle material, say like cast iron, it has excellent damping capacity. It will damp out the vibrations, whatever the vibration generated in the machine, and it will transmit a little vibration to the foundation or ground. So before discussing this machine part subjected to static loads, here I wanted to discuss about the stress strain diagram for ductile material as well as for brittle materials. So what all the materials comes under the category of ductile materials? Say steels, alloy steels, super alloy steels, whatever the steel it may be. They're all, we can treat them as a ductile materials. Under the heading of brittle materials, we have cast iron, glass, brick, ceramic, etc. So this is the stress strain diagram for a ductile material. So this diagram was constructed with the data obtained from tension test. So we have to take a sample of ductile material, say steel. We have to make it as a sample that was tested in a universal testing machine. Every instant of load, we have to record the stress and strain. With the help of that data, we can able to construct a plot like this. So for plotting this stress strain diagram, we have to plot stress on the y-axis, strain on the x-axis, right? After plotting this curve, so we have to locate in various points on this curve. So this is the first point. A, this is called proportional limit. Proportional limit, where the stress is proportional to the strain. And the next point is elastic limit. Point B is elastic limit. At this point, when you remove the load, the material goes back to its original shape. That point is called elastic limit, where this curve slightly deviating from its straight line position to a curve. And the point C and D, they are called upper and lower yield points. Upper and lower yield points. And the corresponding stresses are called yield stresses. Here we can notice one thing. So here there is a kind of deformation, or we can say strain, without appreciable increase in the stress level. Generally, the material strain, when there is an increase in the stress or whether there is an increase in load. But when the material is reached its yield point, at that yield point, failure of the material going to start. Right? That is the indication. So without appreciable increase in the stress or a load, there is an appreciable amount of deformation. Right? A point C is called upper yield point and a point D is called lower yield point. and point E is the ultimate point, and stress at this point, what we can say is ultimate stress. So finally, if you are goes on improving the load on the specimen, at a fine moment, it is going to break into pieces. So point F is the fracture point. Point F is the fracture point. Okay. So this is the stress strain diagram. So with the help of this curve, we can estimate the yield strength of the material, we can estimate ultimate strength of the material, right? And by calculating by some mathematical mean, if you calculating the area under the curve, that gives the toughness of the material, right? Toughness means the energy absorbed by the material up to its fracture. That is called toughness. Generally, ductile material, they are going to absorb huge energy before its failure. Okay. So from this stress strain diagram, what we can understand is, for a ductile material, yield stress is the critical stress. Yield stress is the critical stress for our ductile materials. So in contrast, we can see this stress strain diagram for a brittle material in the second case. And you can see this striking difference between this stress strain diagram of a ductile material as well as for a brittle material. So as we continue the load, no doubt the material undergoes deformation, but at a fine moment, it will break. There is no yielding in the case of brittle material. There is no yielding in the case of brittle material. Suddenly it will fail, right? And by some mathematical means, someone calculates the area under this curve, that gives a toughness. Now, see, literally you can see this area under the stress strain diagram of a ductile material as well as for a brittle material. The area under the stress strain diagram of a ductile material is very large compared to the stress strain diagram for a brittle material. So from this, again, what we can infer is the toughness of a brittle material is very low compared to ductile material. Suppose if you wanted to design some machine components using brittle material, for a brittle material we can consider its ultimate strength, or we can say ultimate stress. Ultimate stress is the critical stress for a brittle material. Ultimate stress is the critical stress for a brittle material. So these points we have to understand for a ductile material as well as for a brittle material. When we wanted to design machine components using ductile material, we have to consider yield stress is a critical stress. When we are designing components with the help of brittle materials, we have to treat ultimate strength as the critical stress, right? So next, so we have to discuss about factor of safety. Factor of safety. What it is? So factor of safety, it is the ratio of it is the ratio of critical stress to the working stress, or you can say permissible stress, right? Factor of safety is the ratio of critical stress to the working stress or permissible stress, or you can say design stress, right? For designing ductile materials, with the ductile materials, we have to consider yield strength is a critical stress. Yield stress is the critical stress, and sigma, that is called permissible stress or working stress. Or permissible stress or working stress, that is the ratio of yield stress to the factor of safety. This factor of safety value is always greater than 1. This is always greater than 1. Understood? So when you are designing for ductile material, in such a case, factor of safety is the ratio of ultimate stress to the permissible stress, or you can say working stress, or you can say design stress. And then in the case of designing of components with brittle materials, permissible stress is ultimate stress to the factor of safety. Right? So factor of safety is always greater than 1. Right? If the factor of safety, suppose say it is a larger value, so what is going to happen? If the factor of safety is a larger value, the permissible stress will be lower. Permissible stress will be lower. It means the size of the machine part going to increase. So this appropriate selection of factor of safety value, it is purely depends upon experience. The person who is having vast experience, in the case of design engineering, on his experience basis, he may select appropriate factor of safety. The fellow who is newly employed in this design area, he may consider higher factor of safety. He may select higher factor of safety. It means that the selection of factor of safety value, it is purely depends upon the experience. There is no hard and fast rule is there for calculating or for defining the factor of safety, for setting the factor of safety. Okay. So next, so after discussing this factor of safety, now we have to go for design against static loading. Right? So machine part, or you can say machine component, when the machine is on or when the machine is in the working condition, the parts of the machine, they may not be subjected to same kind of loading condition. Maybe one component is subjected to static load, one component may be subjected to dynamic load, another component may be subjected to impact load. Understood? So first we have to discuss design of components against static loads. How we are going to define the loads types? We can say types of loads. So we can define into 3 types. One is static load. Number 2, dynamic load. Third one, impact load. What is the static load? In this static load, in the static loading condition, that machine component is subjected to a constant value of the load, constant loading condition, constant loading condition. It means that magnitude and its direction not going to change with respect to time. That type of loading, what we can say is static loading condition, right? See, this is one machine part. It is subjected to a tensile load of 100 newtons. 100 newtons, tensile load of 100 newtons. I can say this component is subjected to static load. In the case of dynamic load, the magnitude and the direction of the load going to change with respect to time. The magnitude and the direction of the load going to change with respect to time. That kind of loading condition, what we can say is the dynamic loading condition. So majority of machine components in the present scenario, they're all subject to dynamic loads. And very few components, machine components, are subjected to static loads. Right? Impact load. So impact load, other words, we can call it as sudden loading condition. Right? So a huge load going to fall on that component or on a body from certain height. So that body is experiencing a huge shock. That kind of load, what we can say is an impact load. Okay? Yes. Now, let us consider machine parts subjected to a static loading condition. So let us see, so what are all the types of stresses going to be induced if a component is subjected to static loads, or you can say steady loads. So here the magnitude and direction of the load is not going to change with respect to time. So I am going to give a simple example. So this is a machine component which is subjected to axial load. I can say F. Some force F is acting. Let us say it is a circular bar whose diameter is D. Right? So this is the circular area which is resisting the load. So this axial load going to induce direct axial stress sigma, that is given by load divided by area. So that area which is resisting the load is a circular section. We can calculate A is equal to pi d square by 4 meter square or 2 millimeter square. So ultimately we can define the stress in terms of some Newton per millimeter square or Newton per meter square. Right? So direct normal stress going to induce in a machine component when this member is subjected to axial load. In converse, if it is subjected to compressive load also, if this component is subjected to compressive load, so in this case also, this element is subjected to compressive stress, right? And we can treat it as a compressive normal stress. Again, that will be calculated load divided by area. So area, this is the circular area which is resisting the load. Understood? Right. Now, so let us consider one body, I can say machine part, subjected to eccentric load, or you can say P and E. So E is the eccentricity. So in the earlier example you have seen that machine component is subjected to only axial loads. It means that the line of application of the load is along with the axis. That's why that the previous type of examples are called axial loaded products. Now, a machine member which is subjected to eccentric load. How could we say this is a member subjected to eccentric load? Very simple. So this in this diagram, the line of application of the load is the distance away from the axis of the member. Right? The line of action of the load is a distance away from the axis of the member, right? A small eccentricity exists between the line of action of the load as well as the axis of the member. So E is called eccentricity. Understood? So in such a case, we should learn so what type of stresses going to be induced in this member. So here we are going to follow an analogy. So here what we are doing is we are going to introduce forces, I can say P1 and P2. P1, P2, they are identical forces. Their magnitude is the same, but direction is reversed. Right? So P1 is equal to P2 is equal to P. So P is the external load. I am reducing the two axial forces of equal magnitude in opposite direction. So because of this, the net effect on this member is zero. Net effect on this member is zero with introduction of two equal and opposite forces. Right? Now, to consider the effect of force P1. Now consider the effect of force P1. So P1, which is acting through the axis, right? So this load, it is going to induce a normal stress. It is going to induce a normal stress, or you can say axial stress. So axial stress, or you can say sigma A, is load divided by area. Load divided by area. What is this load? P1 by A. P1 nothing but it is equivalent to the P. So much of Newton per mm square. Okay. Now the contribution of P1 is over. Now in this diagram we can find two forces. One is P, another one P2. See, these two forces are separated by a distance E. Right? So this P and P2, they form a couple. Right? This P and P2, they will form a couple. They form a couple. That moment of a couple is given by P into E. Moment of a couple is given by the product of force multiplied by eccentricity. Right? So this bending moment going to induce a bending stress in the member. It is going to induce a bending stress in the member. So bending stress, because of this bending moment, it is given by the ratio of M by Z. What is Z here? Section modulus. Z nothing but it is the section modulus that we have to calculate the section modulus depending upon the geometry of cross section. Cross-sectional geometry. Based on this cross-sectional geometry, we can calculate Z, section modulus Z. Okay. So this we can calculate like Newton per meter square or millimeter square. Right? So finally, so this axial stress, it is going to induce a normal stress, and this because of this bending moment, so there is a bending stress, and bending stress also it is treated as a normal stress. Now the resultant stress in this member, that is also a normal stress, that is the algebraic summation of axial stress plus stress due to bending. Stress due to bending. So this is how we can calculate resultant stress in a member which is subjected to eccentric loading. Yes. Now, let us consider a beam. Maybe it may be a circular section or triangular section. So the cross section may vary for this beam. Let us say L is the span of the beam, and let us say load is acting at the center of the beam. Right? If you draw its bending moment diagram, maximum bending moment going to occur at the middle of the beam. Right? That is WL by 4. WL by 4. Once you know this maximum bending moment, like WL by 4, you can calculate normal stress induced in this beam, that is given by M by Z. M by Z. What is Z? Again, this M stands for bending moment. So we have to consider maximum bending moment, right? So for this example sake, I have taken a simple case, that is a simply supported beam carrying a center point load, right? But you can take any kind of beam. You try to draw shear force and bending moment diagram and try to find out at what section maximum bending moment is acting. You calculate that value. So in the calculation, you have to consider this maximum bending moment. Maximum bending moment. With that maximum bending moment value, you can able to calculate the stress, right? So that localized area will be subjected to stress, huge stress. Okay. So this is stress you can calculate by dividing bending moment to its section modulus. We can calculate bending stress. It is in Newton per millimeter square or Newton per meter square. The section modulus generally it is given by I by Y. I by Y. What is I? The moment of inertia of the given area. Moment of inertia of the given area of cross section, or we can say second moment of area. And Y nothing but the distance of the extreme fiber from the neutral axis. Distance of the extreme fiber from the neutral axis, that is called Y. So this is millimeter cube section modulus. We can give a Newton millimeter cube or meter cube. Okay. Yes. So this is how we can find out bending moment, bending stress, or you can say normal stress, if a member is subjected to a bending moment. Now consider another case. Where a member is subjected to torsion, turning moment. Let us say it is a circular shaft of diameter D. It is a circular shaft of diameter D, so which is subjected to a turning moment. So this is a turning moment. Because of this turning moment, or we can say twist, shear stress going to be induced within this member. Shear stress going to be induced because of the turning moment, or we can say torque, right? So in order to calculate that intensity of the shear stress induced in this member, so we have to make use of torsion equation. T by J is equal to G theta by L is equal to tau by R. Tau by R. T by J is equal to G theta by L is equal to tau by R. So here J stands for turning moment or twisting moment, and J, this is called polar moment of inertia, and G, modulus of rigidity of the material, and theta, angular twist, and L stands for length of the shaft, and tau is the shear stress, R nothing but the radius. Okay. So now let us have a relation between T by J is equal to tau by R. right? So what we can say, T is equal to J tau by R. Tau by R. So J, what we can say is I by 32 D power 4. So this is for circular section. Pi by 32 D power 4, where D is the diameter of the shaft. This is called polar moment of inertia. So we can write T is equal to pi by 32 D power 4 tau, or nothing but it is D by 2, or nothing but D by 2. So it becomes 16, and this is dq. So what we can say is pi by 16 tau dq. This much of Newton meters or Newton millimeters. Okay. So from this you can have the deduct the expression for shear stress, that is 16T by pi dq. 16T by pi dq. So Newton per mm square. Newton per mm square. Right? So because of this turning moment, shear stress is going to be induced within the member. Understood? Yes. Suppose a shaft of diameter D, if it is subjected to bending moment, any member it is subjected to bending moment, bending stress is going to be induced. But how to derive the expression for the bending stress if a member is subjected to bending moment? So if for the sake of example we have taken a circular shaft, so here we can use bending moment equation. This m by I is equal to sigma by y is equal to E by R. So let us make use of this part of the equation. So m by I is equal to sigma by y, right? Sigma is equal to m into I by y. So I by y we can say z. I by y we can say z. Okay. So for this, so z is equal to I by y. So for the circular section, what is this moment of inertia? Pi by 64 and d power 4. And what is this y? D by 2. So d by 2. So 32 dq. So this is z is equal to pi by 32 dq. So what we can write is, so this the bending stress within this member is 32 m by pi dq Newton per mm square. Newton per mm square. Right? So this is how we can calculate the nature of stress that is induced in a member which is subjected to twisting moment as well as bending moment. So this is very important from our subjective point of view, right? We have to note the expressions, then how to calculate the intensity of shear stress when a member is subjected to torsion, then how to calculate the bending stress when a member is subjected to, particularly a circular member shaft subjected to a bending moment. So these are all the simple expressions. So complex loading condition. बच्चे कौन है बच्चे जरा स्टॉप कर दो लहाज़. So next case is design of machine part when it is subjected to combined loading conditions, or we can say complex loading condition. So this phenomena of a complex loading condition graphically we can show with the help of this diagram. So here the machine member is subjected to axial load, torsion as well as bending moment. See, in such a scenario, how to design this component? So this axial loads as well as this bending moments, they are going to induce a normal stress in the member, right? So this axial load going to induce a direct axial stress, and a bending moment that was induced in this member because of this point load, right? The summation of this axial stress and the bending stress of what we can say is that is the resultant normal stress induced in the member, that is the summation of direct axial stress plus bending stress. At the same time, this shaft or a machine member, it is subjected to torsion. So because of the torsion, some shear stress is going to be induced. What we can say, we can calculate the intensity 16T by pi dq, right? See, in such a case, there is a mathematical model to represent a complex loading condition, or you can say combined loading condition. So that will be shown like this, a mathematical model. So it is a bidirectional loading condition. Right? So it is a bidirectional loading condition model. This component is subjected to normal stresses in the direction x and y. Sigma x is the normal stress in the x direction, and sigma y is the normal stress in the y direction, and tau xy is the shear stress that is acting on the planes. Right? So in such a case, the principal stresses principal stresses we can calculate in this way. Sigma 1 comma 2 is equal to sigma x plus sigma y by 2 plus or minus square root of sigma x minus sigma y by 2 whole square plus tau xy square. Right? And the sigma 1, if you put in between a plus sign, we can able to calculate major principal stress. Major principal stress. Major principal stress, that is sigma x sigma y by 2 plus this is the sigma x minus sigma y by 2 whole square plus tau xy square. Right? If you put a minus in between, you can calculate minor principal stress. If you put a minus in between, you can calculate the minor principal stress. So, major principal stress that is greater than minor principal stress. Right? But where this maximum principal stress is going to act, how to locate the position of a principal planes. So principal planes could be calculated using this relation, that is tan 2 theta is equal to 2 tau xy by sigma x minus sigma y. Right? So this is with this we can calculate theta. This gives position of principal plane. Yes, I can show this is the angle theta. You can say sigma 1, and sigma 2, sigma 2. Right? And theta is the position of the principal plane. And these planes are called the principal planes. On the principal planes, we find only normal stress and there is no shear stress. Right? And there is expression for calculating maximum shear stress that was induced in a member when it is subjected to a combined loading condition. For that also we have an expression, that is square root of sigma x minus sigma y by 2 whole square plus tau xy square. So that is the expression for calculating maximum shear stress. But way to show the position of a maximum shear plane. Maximum shear plane is, that is 45 degrees to the principal plane. Maximum shear plane is 45 degrees to the principal plane. Yes, this is 45 degree. Yes, there we can have maximum shear stress, tau max. Maximum shear plane is 45 degrees to the principal plane. So this is how we can calculate the intensity of maximum normal stress induced in a member when it is subjected to a combined loading condition, or you can say complex loading condition. It means that is the combination of normal stress as well as the shear stress. Right? At the same time, there is an expression for calculating the maximum shear stress induced in a member that is subjected to a complex loading condition. Right? See, these two extremities we can calculate with the help of expression when a member is subjected to a complex, or we can say combined loading condition. Okay? So thank you very much.